So.
Okay.
Let me recap what we said. So I want to find a way to implement quick measurement on a many-body quantum system. And the protocol that I was suggesting here was the following. At this level, it's still very generic, so we have a lot of degrees of freedom. And we start from a system and then signal. We entangle them through some on-site unitaries, and then we measure the axilla on a given basis. And the goal would be to probe the entanglement and the correlation function on the system. Just to connect to the class operators that we considered before, I've shown that if the ancilla is a simple structure, like if that's the product state, then one can choose the unitary operator such that at the end so the measurement operator is this form side by side, actually depending on the specific NJ. So this we can exponentiate and get something like e to the beta and the OJ, where branch beta is the So this is just an example to show that really the amount of entanglement that you have between the system and its degrees of freedom corresponds to the measurement strength. Now, in general, of course, it's hard to get a closed formula for all the values of U, and it can be in the case of a simple product state. So what we usually do is an expansion in the regime of small U. In the regime of small entanglement between the system and its degrees of freedom, one can basically take this object and do an expansion in the limit of small u. And in general, what we find is the following.
Sorry, before that, can I ask you, so if I understand correctly, here you're saying you start from a product with a product state, you do local measurements in the X spaces after the unitary U, which is essentially a control of dynamics. But there is no dynamic, like on the horizontal axis there is no evolution, right? Just then we call there is a unitary and the state is fixed.
Exactly. Yes. So the difference between measurement criticality and measurement induced transition is that there you have an interplay between dynamics and measurements. Here we have single shot measurements.
Okay. And we find that for any measurement outcome, the state becomes entangled. Or because you said the interaction strength becomes equal to the entanglement you get.
So this is the operator, actually, is the operator that acts on the system.
Okay.
So what I said is that the measurement strength of this operator that acts on the system can be related to U, which is the amount of the entanglement between the system and the ancilla.
A non-entanglement between the degrees of freedom of the state side, but is entanglement vertical entanglement.
Yes, the entanglement between the two. I mean, because this once we measure, it's out of the gates, right? It's this element. So it's triggered if you want. Like, once we measure this product state, so the interesting remaining part is this derivative operator here, which acts the original system. So then the question is, what is the entanglement of this object here, like of this derivative operator on the system? How this derivative operator acts the original properties of the system.
Okay. Which you still have to find out. But,
Exactly. Okay, so this is just to convince that doing this protocol we can recover the result from the cross operator. And actually we don't want because let me try to pass this example. So now the plan would be to try to understand how this translates more in a theory language, and then I will do the example for easing and see explicitly what happens. So just one comment, if you do an expansion for small u, like up to order u square, one can prove that this psi m is optimization e to the u square sum over j and j or j. But we should call it actually AJ, because it depends on the measurement factor. It's a function that depends on the measurement factor. This is the leading term in the regime in which, let's say, psi of A is a low entangled state. The nice thing is that if you choose, for instance, the sigma to be a critical state as a system, you can also engineer some long range which is somehow, it's like if I have an entanglement over here and I have to take into account of the entanglement present there, and the way in which you take it into account is reading this protocol and obtaining a non-local measurement that you can do here.
So by low entanglement state, you mean just not volume low? Because you say this expansion is valid for.
Yeah, you get this form in the regime where, so if you think about some ground state physics of local Hamiltonian, let's say, the entanglement can be either low, or you can have some logarithmic growth at a critical point. So by low entangled, I would be the analog phase.
Okay.
Not even logarithmic.
And so in this case, I'm not sure if you observed in that A of j, but it doesn't matter which operator which is there for the Anchila system, because
yeah, it's absorbed.
Okay, it's absorbed there. It doesn't depend.
So basically, this falls into the also the when we talk about post-measurement state, I will refer to something like one over normalization, e to the beta, 2 over j, and j, or j psi. And if you're interested about in how to get non-local measurement, okay, so now I want to translate this into a field theory language. So how does a weak measurement or this operator translates in the field theory language in particular we will do a mapping with the impurity problem. So the idea is the following. I mean, at this point, we just need that psi is a quantum field theory, not necessarily a conformal field theory. So a quantum field theory, a conformal field theory is a quantum field theory, and when the quantum field theory is massless, it can have also conformal invariance, so being described by a conformal field theory. That's the generality. So now we just need a state which has a nice low energy distribution. And the regime, the framework that we use is a particular formulation of correlation function. So I will just do tell me if it's something obvious. I will do a recap of how to write down a particular correlation function. So we take start a state, say, psi, that is then it's a quantum field theory, and we can express this as the limit when t goes to infinity of 1 over z raised e to the minus t h over 2 then e to the minus 2 h over 2. Now basically the limit t goes to infinity. This is projecting into the bra and this is projecting into the cat. And this is just the partition function to ensure the normalization. And now we take the continued limit. So I will use the graphic notation, the note, for instance, psi expectation value.
Sorry. Here again, psi is the Gauss state of H.
Yes, sir.
Okay.
When I say continued limit, we will see an example more explicit for the ideal case, but the idea is that we have some macroscopic operator on the lattice, and this you can map to some field in the theory. In the continuity. And so this will become just the limit equals to infinity of 1 over 3 raised into again, this will be a calligraphic stage. And now, I mean, the way to get the particular formulation of this correlation is to do a factorization of this exponential, so to split into more contribution, and we apply an identity resolution, such that at the end, this becomes the integral d phi e to the minus s of phi and a the tax at tau equals 0. So we have x tau is time, okay, but tau is independent time, because here is Euclidean evolution. And now you can think of the imaginary evolution from minus infinity to 0, that's the value of my cat, okay, that's here. Then you insert your operator. Time equals 0, and then the imaginary evolution from 0 to plus infinity, which corresponds to the value graph. This is usually, if you write down a correlation function in the particular formalism. Now what we have to do is something very simple because so let me for this date each of them. Okay, so basically each of them is the object here. And if we do it, basically what we have to do here is shifting A to EHN, A, EHN. You agree with this? And we just have to, let's say, rescale or modify psi by different here. And so if you repeat the same steps, basically you will find that now, rather than just having S of phi, since here we have to insert also this into the H1 and into the H1. Here we get S of phi. Let's see how. Plus S of m. Okay. S of m is into dx or x. So you can see that doing a measurement basically corresponds to insert a defect line. At time equals 0, compared to the what happens without this measurement. And this basically is the key observation to study measurement after critical. Like understand that the weak measurement that you are doing, so this operation here, is simply introducing a defect line in your x tau space-time. And then what we're interested in is computing correlation function along along the defect itself.
So can we clarify? So E to the HM is basically the cross operator applied to the psi, right? Yes. Okay. And then how are you interpreting the operator A that you're trying to compute expectation value of? Like this A is a generic operator.
This A is a generic operator, like Z or ZZ.
Okay, and then how do you plan, I guess, to apply in this context, like to measure correlations? Or,
how do you plan to?
like, why are you trying to compute expectation value of some operator?
Right, because you want to probe the properties of this post-measurement wave function. And the main properties that we probe are correlation function and
okay, so you will use you will take A to be a correlation function or something else.
yes, the correlation function, yes.
Okay, and this trick allows you to express these correlations or other features in terms of, can you?
Yes, so basically once you realize that, so you're given with the fact that A just corresponds to introduce, let's say, if you want to compute the correlation function of A in the particular language, just corresponds to introduce A at time equals 0, fixed imaginary time. Okay, and then we observe that rather than measuring A, we want to measure a dress version of A, where the dress is given by the measurement operation. Now you can see that this operator here, so if we act also type of 0, really as A, With the difference that now HM is defined as some other J, J, or J.
Is that kind of like a hybrid revolution away, or can I not imagine it that way?
But it's in Euclidean time, and it's not really an evolution. Like here, we are really projecting into the ground state of H. This H is the Hamiltonian for which side is the ground state. Here, we are really just reshifting shifting A by some non-unitary operator that will act at all special point just because it's a sum of single side operators.
But if I understood correctly, first you wrote this expectation value of A on psi, but you want to compute it actually on psi m.
Yes.
So that's why this HM appears.
Yes.
Okay. So that's the general formula, but then you want to apply it on psi m.
Yes.
Okay.
So here, here this is but then you see that the limit T going to infinity is really just refers to the preparation of this graph here and this gap here. So this H of n is just changing the A. And the idea is that then we put, it's like we assume that like H and HM can be collected in a single exponential, just with the difference that the HM doesn't depend on the T. So this is why it won't act at all extra space-time, but it will only enter as a defect line.
Yeah, but you don't care about the rest. Right?
No,
so
we don't
you are
care
at
about
zero
the rest.
temperature, so you are only.
Yeah, we can work about it. Okay.
I mean, we could, in principle, forget about the temperature at all. We could have done, like, do you really need to do it starting from the.
No, just to get the particular.
Yeah, the ground state.
Yeah, it's just yeah, but it was a more natural way.
Yes, it's not that. Sometimes it's easier, actually. It's really simple.
Yeah, so the main message is weak measurement equal defect along the imaginary time. And maybe I would like to stress that and I really think that if I have a Hamiltonian H and I perturb it locally, that's the same thing. I mean, yes and no, in the sense that they are the same thing if then you plot the correlation function in time, in the imaginary time, along the side where you perturb your Hamiltonian. So this is something.
So when you say locally, you mean locally in the sense of the time correlation, or locally?
Yes.
Okay. So basically, because it's you are acting everywhere space and space.
Everywhere, yes.
By timeline, you are frozen. You only use the of the.
At time, exactly. Is it clear?
Just to have a comparison, so you said weak measurement is a defect line, and a strong measurement instead would correspond to what?
So, in the limit of strong measurement, okay, we see that in the case of Ising or Latinger, let's say not the cases that I've studied so far, there is not really like an intermediate fixed point of beta after this you change the physics. It's a continuum algae flow as a function of beta. But strictly speaking, in the regime in which this beta goes to infinity, really infinity, then you just get MJ basically, no? You project, like if you are projecting into the ground state of this Hamiltonian here.
So you basically you start from beta equal to 0, or close to 0, and you follow the flow. And you say there's nothing really happening in some model, I suppose.
Yeah.
As you follow the. Okay.
Yes, at least for easy Latinger, I would say all the minimal models, nothing interesting factors and final value of beta. To observe something non-trivial happening at final value of beta, you need to or have something non-local here. And for instance, if you have something non-local here, and you start from some easing the downside in the trivial phase, then you can get some non-trivial transition with the topological phase at final value of beta. There will be a difference, but you need something which is non-local. Until you are local, it's like if you are staying always in the same phase, basically. So you get the flow, the function of beta, and nothing particularly interesting happens at beta equal to infinity.
Do you expect the beta equal to infinity to, does this agree with the numeric if we do it exactly? Because we also assume that we could express in this exponential form, which needs beta to be small, no? Or maybe I'm not.
Exactly, so unless you choose the case in which this is really another state, so then this identification is true for all the value of beta. If we start from a state which has some low entanglement, then this expression will be also in the regime of small beta. But I mean, at least in all the papers that I've seen, it's very common to choose an ancillary similar state because the aim is to do that. No, I think the aspect of the limit beta to infinity can be between the thermodynamic limit and the limit beta to infinity. So one can ask, do these two limits commute? And I think these limits don't commute. Neither, I wish I would happen for easing. I think if you are at n equal to n is finite, and then you get beta going to infinity, you really get just a product state. However, I think if you take n infinity first and then beta going to infinity, then you can get something non-trivial. So this two, I mean, the order of these two limits is a bit tricky, and then let's explain. So I will show it for you.
This is the post selected. So you already know the result, right?
Yeah, I'm choosing them.
Okay. So if you just if you don't want to select this, and you going to have. So if you can you follow what happens in the not post selected case?
So yeah, it's an interesting question.
So the question would be, I guess, twofold. As in the magnetic use phenomenon, right? You can either average over the possible results, that's one possibility, or assume that you analyze entanglement and correlations in every single outcome and then average these entanglement and correlations in every single.
Exactly. These are the two. I mean, at the end, these are always two phases of different selection, if you want. One at the level of a single trajectory, like a single measurement outcome. Like I have a measurement outcome, and then I ask what is the behavior in a specific outcome, which can be on uniform or it can be a typical outcome. Or you can ask what happens if I consider quantities like sum over n, Pn, psi m, or psi m. Actually, tomorrow one part of the lecture will be about it's not showing that linear averages are trivial, like you just recorded the later. And so what we do is compute predicated quantities. But the results about predicated quantities are very complicated. Now I'm trying to do something for Latinger with a little bit more tomorrow. It's pretty hard.
What are the replicating quantities?
So rather than averaging, for instance, so this quantity
Depends on the state itself, like just
depends on the first moment of the state. Like not just what I'm saying. But you can ask, for instance, this is it's like it's depending on the like cyan replicated twice. Okay? That's a product of cyan. Go ahead. Yeah, so if you want to extract monumental criticalities, there are two ways. Or you post an specific outcome, and this is what we will do now for icing, and then show you tomorrow what happens for it, just to get something of to get an idea what will happen in the experiment, or you look at replicated quantities. I think they are equivalently difficult from an experimental point of view, but this case it's much easier than like for replica, for the case there are a lot of results. For the replicated case, I don't know. And also when you measure new space transition, no? Computing replicated quantities, unless you have the like you average it with this Vanguard calculus, and also there extracting yeah. We usually use some netting for statistical models, and then you are able to solve the new statistical model. Just a practical problem. Okay. Are we ready for the meeting? Are you familiar with using conformal theory?
Yeah, not really, not too much.
Okay, I will do it. I had an obsession about critical states already in my PhD because Pasquale has worked a lot on conformal field theory and analysis. But I think when I started working on this, my obsession with critical systems even increased. Okay, so we start from the thesis conformal field theory. Except that, so I write down the Hamiltonian for sin. Okay. So this Hamiltonian, I put the magnetic field, the transverse field on the x direction, and I work in the regime of J greater than 0 for the magnetic coupling, and we can write down the phase diagram as a function of the ratio of H over J. And when H over J is smaller than 1, then we are in the ferromagnetic phase. So in particular, at H over 0, we have to generate ground state, go up and go down. As we increase the ratio of H over J, basically, this part dominates, and then also is given by the configuration where all the spins point along the x direction. And when H over J is exactly equivalent to 1, the system undergoes the second order phase transition and becomes critical. So it's exactly here where we have conformal field theory. Describing the properties of the system. Actually, already from here, I can make a comment. Actually, I could have kept this picture. Okay. product state such that we have access to all the values of u. And I want that the system is the ground of the physical return exactly the critical phase. Now you can ask why? Why do we start from a different phase? And the reason for which I think it's interesting to start exactly from the critical point is because at the critical point we have this conformal field theory. So we have a lot of structures which determines, for instance, power decay of correlation function and these kind of things. If we start from the paramagnetic phase, for instance, it's like having a massive quantum field theory. And if we have the defect, the correlation function decay exponentially. If you have the defect, they will still decay exponentially, like nothing really new happens. So it's much more interesting to look at the critical point because it's there where the physics is not trivial and we want to see how it transforms under these non-unitary interactions. So something that I really like when I talk about magnetic system is to have in mind a clear mapping between what happens in the lattice and what happens in the continuum limit. And we can write down a sort of dictionary between microscopic operator and macroscopic operator. So the Z Pauli spin operator corresponds to the field sigma of x. And this field sigma of x is called primary field. I mean, it's not necessary that you know what primary fields are just a special class of fields in a conformal field theory. Usually people say that these transform nicely under conformal transformations. I don't think it makes a lot of sense if someone is not really expert on conformal field theory. You can think that knowing the class of this conformal field theory, there are some, let's say, particular field. One is sigma x. And the reason for which one can do this identification is because, for instance, Z is odd under zero symmetry, and the same thing is true for sigma. Sigma is also odd under zero symmetry. So, odd under zero. In general, symmetries play an important role. Like if you have a theory of the lattice and then you want to determine what are the properties of the underlying field theory, let's say keeping track of the symmetries is the guiding principle in order to go from one side to the other. Another principle of this identification is the behavior of relation functions. Like Vj is K, Vk says J minus K to the power of minus 1/4. And if you look at the correlation function of sigma d or sigma x, this Vk says x to the power of minus 1/4. Of course, they should decay in the same way. Maybe there is some there is some universal term in the factor of this, but basically, this is what your field theory is telling you, and then given a field theory, you have different microscopic realization of the same field theory, and easy is one of these. The fact that this has a power decay of 1/4 also allows us to define the concept of scaling dimension of an operator. So the scaling dimension So for sigma, for instance, the scaling dimension is 1/8. Basically, the power law is twice the scaling dimension. So as for like easing like in the Newtonian here we have V and X. Also the picture level we have two fields, sigma and what we call epsilon. Okay, so Z corresponds to sigma, which is odd under C2, while X corresponds to epsilon, which is even under C2. And okay, you can think of epsilon as follows. So if, for instance, you perturb your Newtonian and you add an external, adding an external corresponds to change the magnetic field. And so if you change the magnetic field, like for instance you add H prime Xj, then you have a new field, H plus H prime, and you go to the parallel phase, no? You get the electrical phase. Same thing for epsilon, like if you have the action of heating and then you have an epsilon perturbation, epsilon is the field that drives you out of criticality, that basically introduces a mass in your system. Like introducing a mass corresponds to change in magnetic field. Again, we can look at the behavior of correlation function, like SK connected correlator, in case as J minus K to the power minus 2. And epsilon 0, epsilon s, decays as s to the power minus 2. So we can introduce the scaling dimension of epsilon, which is so this is what you need to know for what I want to tell you about the behavior of correlation function. Just we have the system, which is the ground state of the heating Hamiltonian, exactly the critical point, and the critical point we can write down a dictionary between the power spin operator and the things in the continuum limit, which are sigma, that has the same symmetry properties as Z, and epsilon, which has the same properties as X. So we can exploit this dictionary in the following. The other things that I would like to mention is the behavior of the entanglement. So I take the ground state of H, and usually when I compute the entanglement, what I have in mind is like a state living in a hyperspace that factorizes into the hyperspace of H, the third product, the hyperspace of the complement of H. Right? So, for instance, I have a system living on an infinity line, and I consider a subsystem A. If I look at the entanglement of A, so S of the subsystem A, for the ground state of the easy model, it indicates as 1 over 6, or 5.
But this depends on the boundaries, right?
Here I have a system in the limit. If, for instance, you have a system which is attached to the boundary, then this will become 1 over 12. While if you have a periodic boundary condition, you get again 1 over 6 log. I mean, here then the system size you have the core length. L over pi sine pi L over the log of the core length. And I actually been giving this information about the environment behavior. I'm, let's say, hiding another safety data that you have, which is called central charge. So in general, for a critical system, this formula is C over 3 log A. And for eating, C is a vertical column. So basically, we have identified three universal data of the eating which are the central charge column, the spherical dimension equal to 1/8, the spherical dimension of sigma equal to 1/8, and the spherical dimension of epsilon equal to 1. So the question is, how do these universal data change after measurements?
In which sense they are universal?
They're universal in the sense that these are results that fall at the field theory level, not the level of the performance field theory. Then, whatever is the microscopic realization that you are choosing that falls into the easy universality class, will have this behavior. So, for instance, today we will describe in detail easing. Tomorrow we will see what happens for Rydberg. Rydberg is a completely different model, no? It's not even described in terms of we describe in terms of art proposals. Still, it has the same long distance behavior. I think this is the power of critical system, like the fact that they describe a lot of microscopic systems according to that universal class.
But when you do measurement, how do you know that the new state is also critical?
Exactly. This is what you're talking
Because you can define these things only for critical states, right?
Yes, exactly.
Okay.
No, indeed. Once we apply that defect, you go away from the original critical spot. And the question is, where do I end up? Okay, so now we will study two cases. The first one is where the measurement operator takes a form into the beta from over j, xj, side side c, the opposite of the here I'm doing a constellation, like I'm assuming that Nj is equal to 1 for the sides. Now, using the fact that x corresponds to epsilon, we can immediately break down what is the defect line that we have. Like what we call S or M. Basically becomes an integral in the x of epsilon x. And now at this point we can ask, okay, epsilon is plane dimension 1. D of x is plane dimension -1 in units of So this operator here is marginal. It's a marginal perturbation. The marginal under normalization group. Because usually in the literature epsilon is a relevant operator because it's considered as a bulk. Not like in the bulk it could be relevant. The point is that when it is in a line, so that's why it's marginal. Now, if you have a marginal perturbation, basically what happens is that you start from your CFT at b equals 0. So you start from SFT at b equals 0, then you turn on beta, and point by point, you create a line of fixed points. So, line of fixed points. And this is true because the perturbation is marginal. Because there are three different kinds of perturbations in normalization. Marginal, relevant, or irrelevant. So if it's relevant, you just flow somewhere else. If it's irrelevant, it means that it's, you don't change the inference properties of the state from which you're starting. If it's marginal, then you have this intermediate case in which for all the values of your RG coupling, so in this case, you get an induced point. So the expectation is that in this case, if you compute the entanglement or the correlation function, they will depend on a specific value of beta. Questions?
So you said depending on the number of beta, you can get a different fixed point. That's what you said.
Yes. Each beta determines.
Depending on the strength.
Exactly, depending on the case. And now, actually, there are several ways to study the properties of these post-measurement wave functions. For me, the easiest way was to use the fact that if you write it in fermions, if you write it in fermionic variables, this xj is basically the number operator. No? It's sum over j and j. And the ground state of the Ising model is the P-type chain with some chemical potential, so it's a Gaussian state. This operator is also Gaussian, and so you can use the techniques of Gaussian states to derive all the properties that you want. And let me write down the properties. So the properties that I'm referring to are of this entanglement and correlations. So the entanglement.
So you said this is a special case of all and j equal to 1.
Yes.
Okay. Not some of all the situations.
No.
Okay.
No, it's a spoiler effect tomorrow. For typical outcomes, actually, it becomes irrelevant.
Oh.
Because it's like these J also have some decay correlations, also have some scaling dimension, and so we have to defend this irrelevant. It actually becomes very easy to study for the element outcome. Just because the most interesting one is marginal, and we know only the values. And the typical ones, where the typical in sample and quality of probability, is irrelevant, and we also know the properties of the original sample.
So if you wanted to study replica, it's
very
okay.
And no, like, or if you square the correlation, you just recover the square of the existing correlation. Indeed, this is one of the, actually, basically, this is the only case that is not regular. So the effect is that the determinant entropy still grows logarithmically. And the leading order is this behavior. So I define this object that I call effective central charge. It's just a factor of the logarithmic term of the entanglement. It doesn't have any returns to the different critical system here. We can try to plot it because the formula is a bit so if you plot it as a function of the measurement step, so we have the effective. So when v is equal to 0, it's 1, no? Because we said that using this universal data, and then it continuously decreases as a function of the measurement step.
When you mentioned these Gaussian techniques for splitting this is this Fisher-Hartwig.
Exactly. So Fisher-Hartwig gives you exactly the logarithm because it just comes from the discontinuity that you have in the symbol of your correction matrix. Here it's important to select n equal to 1 because the system is positionally invariant.
Yeah.
And basically this object here doesn't change the discontinuity. They are always discontinuity k equal 0. And so you can just compute the new connection matrix and apply this Fisher-Hartwig. You have to apply Fisher-Hartwig for the block topics matrix.
Yeah, which is not proven by the.
It's not a theorem, it's a theorem only for the scalar. But here, for using, you always have both the relator of CC and CC diagram. This is why it's a block.
Yeah.
While the easiest cases with only one symmetry, then it's a scalar, and
this is
it's the theorem.
rigorous.
And never seen Fisher-Hartwig fail. Okay, so the entanglement entropy still preserves logarithmic growth, but just with a different factor that has its properties. I'm not very good at drawing, but really it becomes 0 only when it is equal to infinity. Otherwise, it's small but not 0. And the other thing that we want to study is the scaling dimension. So, let delta sigma of beta, for instance, becomes divided by pi squared. So in the limit in which beta goes to infinity, so beta goes to plus infinity, this becomes infinity, and the potential for infinity is pi over 4. Sorry, power 2. And it's becoming equal to 1 because we have 1 over 4. When beta is equal to 0, the potential for 1 is power 4, and so we get
Beta to infinity is lambda equal 1, right?
yes, the projected case. And for beta equal to minus infinity, this becomes 0, and the potential for 0.
Does it mean beta to minus infinity?
It's like, I mean, you can also think that you UniPa selects for only n equal to -1.
You projecting on the other.
Exactly, projecting on the other things. Actually, in this limit, it becomes a sort of gauging state, where the correlation function becomes under 1. This would be the case in which the correlation, the variance, the quantification information increases. Right, because you go from a power decay to some order 1 decay. The problem is that